Okay, hi. My name is Rich Lasinski, and I want to talk to you about projectile motion problems inside cathode ray tubes. Yesterday we talked about how you could figure out the velocity of the electron, and that's going to be your initial velocity. And remember, you have to use the formula V equals W over Q, and then once you have W, W is equal to the kinetic energy of the electron, and then kinetic energy is equal to 1/2 mv squared. And ultimately, that's how you get the velocity right there. That's your initial velocity. And then basically, when that electron goes into these oppositely charged plates in between them right there, if they were neutral, the electron would just continue to go straight on through, as I showed with this red line right here, and they would hit the screen right here. But what you're going to be asked to calculate is how much it ends up dropping or falling down due to the electric force. So when the plates are charged, it ends up dropping down here, deflecting down, and basically we're going to want to calculate what this little drop is right there. What that little tiny drop is. Let me try and draw that differently here. Between here and there. Like that's going to be our x sub y, how much it vertically drops. And how far the electron actually went forward is going to be the length of the plate right here. That's going to be x sub x. So when we do this problem, we set things up similar to a good old projectile motion problem where we have horizontal motion, vertical motion. The acceleration horizontally in the x direction, of course, is going to be 0. But we need to figure out what the acceleration is going to be in the y direction. It used to be negative 9.81 meters per second squared when we were dealing with gravity. But now it's not a gravitational force that's pulling it down. It's the electric field that's pulling it down. So no more negative 9.81. So we need to figure out how we're going to get that acceleration right there. Now, in some problems, like your first homework problem, they actually tell you what that acceleration is. Downward acceleration right here. Just watch your units because they gave it to you in centimeters per second squared. So you're basically good to go. You could do this problem just like a good old projectile motion problem. But sometimes they're not so nice and they don't give you that acceleration. You have to actually figure it out. So let's look at another capacitor problem. Here with the deflection plates, they give you the voltage that's across these oppositely charged plates right here. And they tell you the distance between the two plates, 0.05 meters, 5 centimeters. And basically, you're going to have to do the projectile motion problem, but you need that acceleration. So what's a poor physicist to do? Well, recall, Newton's second law says that if something's accelerating, there has to be an overall net force acting on it. And if we want to get that acceleration, if that's our unknown, so that we could do the projectile motion problem, we're going to need to know the mass of the particle and the overall net force. Well, the mass is the mass of the electron because that's the projectile that's flying through the plates. But what about this force? Well, what's actually providing the force, pushing it down? It's the electric field. Now, this is a little bit tricky because the electric field in between the plates is actually going up. But remember, the electric field shows the direction of the force acting on a positive particle, but we're sending through an electron. So the electric field is actually going up, but the electrical force is actually going down. But nonetheless, the electrical force is providing the net force. So this is an electrical force. It's an electrical force providing the net force. Now remember, if we knew the electric field strength, we would know how much force is acting per charge. And that's what we're trying to figure out. Ultimately we want to get this acceleration. So we need the mass. The mass is the mass of the electron. So we're going to need this force. What's providing the force? Well, it's the electrical force provided by the electric field. So if we rearrange this, we have F equals E times Q. And what's up with that Q? Well, it's an electron because that's what we're shooting through the plates there. So that's going to be 1.6 times 10 to the negative 19th coulombs. Yes, it's negative, but we don't really care about that now because we're just looking for the magnitude of the force. We know the direction. And that 1.6 times 10 to the negative 19 coulombs, that's just one elementary charge, but written in terms of coulombs. So we know how to get the charge. So all we need is the strength of the field. Well, if they give the voltage of the battery connected to the plates and the distance, there's a formula: voltage equals electric field strength times distance. And basically, if we wanted to see where that came from, let's take a quick look at that. Remember, work is equal to force times distance. Well, if we divide both sides by Q, because with electricity we like to talk about the work done per charge, so then we divide this side by Q. That's the same as just having F over Q times D. Algebraically, that's the same. But notice, work per charge, that's the electric potential. Force per charge, that's the electric field strength. And then the distance is just D. So that's where this formula comes from. V equals E times D. So you have to use this formula to take the voltage and the distance here. Use the voltage and the distance to get the electric field strength. And then once you have the electric field strength, where were we? Once you have the electric field strength, multiply by the charge to get the force. Once you have the force, put that in Newton's second law to get the acceleration. And then once you have that acceleration, boom, 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 you have the value right here to go on and do your projectile motion problem with your two columns. Good luck.